Bismillahirrahmanirrahim. In this video we'll learn about techniques of synthesizing voltage ratios. Now let's try to understand the difference between analysis and synthesis. In general, analysis is defined as the procedure by which we break down an intellectual or substantial whole. So we break down any problem to solve basically. This is analysis, and that is what we have been doing in most cases. Whereas synthesis is defined as the opposite procedure, that is to combine separate elements or components in order to form a coherent whole. And generally, operational amplifiers can be employed to synthesize a desired transfer function through cascaded stages. Okay, now let's have a look at this circuit. You can see that the input is at the negative terminal. So this is an inverting amplifier. The feedback impedance consists of a resistor and a capacitor, and the input resistance is a single resistance R1. So we have learned earlier that for an inverting amplifier, the relation between V out and V in is negative ZF over Z1. That is the transfer function Hs. Now if we calculate these two parallels, so ZF will be like this, and plugging in ZF and Z1 is R1. So we get this relation. So this is the transfer function for this circuit. And now if you look carefully, this denominator term will become, when it becomes 0, this will represent a pole. And so we call this circuit to represent pole, or this circuit is used for pole. And just for you to remember, I have drawn a pole here. So this is slightly going on the upside. So this circuit is for the pole, that is the feedback parallel circuit, and the feedback will represent a pole circuit. On the contrary, we have another inverting amplifier. This is also inverting amplifier. But now you can see that the input has a parallel resistance and capacitance, and the feedback has simply one resistance. And Hs in this case is also negative ZF Z1. And now our ZF is RF, but our Z1 is parallel of these two. So by solving Z1, we get this term. And plugging in Z1 and ZF value, the final value of the transfer function, we will get like this. And now since this is all in the numerator, nothing in the denominator, so this term when it becomes 0, it produces a 0, and so this circuit is called, it is for 0. So we have to keep these two things in mind, that for the circuit which is representing pole, the transfer function is represented by this, and the circuit representing 0, the transfer function is given by this. So let's start to explain the questions solved in the book, example 15.13. It says to synthesize a circuit, so we have to make a circuit that will yield the transfer function Hs is equal to this term given here. And from here you can see that this is 10 is a constant, and this is the 0 term, and this is the pole term. So to realize this, we'll need a pole circuit and a 0 circuit. So this can further be written as like this. So this is the 0 circuit, and this is the pole circuit. So we'll first try to get the pole circuit. So this was the circuit we found out to be used to be for pole. And the pole will occur at s plus 5 equals 0. That means at s equals minus 5. And this was the transfer function for the pole that we got in the previous slide. Now we compare these two. Compare the denominator. So this term is equal to 5 from here. And so we can write that 1 over RFA CFA is equal to 5. This term RFA CFA. We are writing A to distinguish the pole circuit. So 1 over RFA CFA is equal to 5. And now we can assume RFA to be 100 kilo. Generally in the inverters, op-amp circuits, the resistances are taken between 10 kilo to 1 mega. Here we have taken 100 kilo. And putting in this value of 100 kilo here, calculating, we can find the capacitor to be 2 microfarad. And now let's plug into the transfer function. This was the transfer function. We have just added A in all of these. And the denominator is equal to s plus 5 from here. So we plug in s plus 5. CFA we have got 2 microfarad. So we plug in 2 microfarad. Then this will, after solving, will become 5 into 10 raised to the power 5 divided by this resistance R1A. So this is still unknown. Now we have found this up to this, and this was the original transfer function. Now we'll go for the 0. You can see the 0 is occurring at s plus 2 is equal to 0. That means at s is equal to minus 2. So this was the circuit that we said we'll be using for 0, and this is the transfer function for 0. So just like before, we write now this in terms of B. We have this circuit we call B circuit. So we just added B. And from here, you can see s plus 2. This term, s plus whatever is this is equal to 2 from here. You can see s plus 2. So this is s plus this term. That means 1 over RAB, R1B, C1B is equal to 2. And here also we assume the resistance R1B to be 100 kilo. And so C1B can be found to be 5 microfarad. So we have found the two values. And now we'll plug in the values in this case. So this is 5 microfarad into CB is 5 microfarad actually. Then we write RBF, and this term is S plus 2 from here, S plus 2. Okay, so we had the result so far. We got the two values of the capacitors and resistors from the two circuits. We got this for the transfer function for circuit A and this transfer function for circuit B. And this was our question, that we have to realize this. So from here we can say that HS is equal to HAS and HBS. That is the transfer functions of the pole circuit and the zero circuit. So let's plug in the values of the HAS from here and HBS. And if we solve, we get this two term, 2.5 minus minus plus, and 2.5 multiplied by RFB divided by R1A and multiplied by S plus 2 and divided by S plus 5. So now again compare with this. This term should make 10. That means RBF over 1A should make 4. So 4 multiplied by 2.5 will make 10. So we can assume a value of RFB to be 100 kilo and R1A to be 25 kilo. So the ratio will become 4, which will complete 10. And so now we have the complete circuit. So now we plug in the values. This is R1A for A circuit, so we plug it in here. These two values from here for the resistance and capacitance in parallel plugged in there. And then we have for the second circuit, these two values for the second circuit, 100 kilo and 5 microfarad. And this is this resistance of B circuit, 100 kilo. So this circuit will now will realize this transfer function. Okay, now let's quickly do the practice problem also. Specify suitable elements for Z1 and ZF in each of the 3 cascade stages to realize the transfer function this. So let's see the transfer function. If you write denominator, this looks like this. And from here you can actually see that S square is representing 2 zeros, 2 repeating zeros, and this is repeating a pole. So we just break it down, and since all our circuits use inverters, and therefore we'll write a -1 here, -1 here, so this will become plus, and this one -20, S plus 1000. So these two are the zero circuits, are represented by zero circuits, and this will be represented by a pole circuit. So let's start with the pole circuit first. So this should be a pole circuit, and then a zero circuit, and then another zero circuit. Same value, same circuit, because the value is S here in both the cases. And we just, for ease, we name them ABC. This was the formula for A circuit. We had seen this in the previous slides. Now comparing this with this, you can see that the denominator term is equal to 1000. So 1 over RFA CFA is equal to 1000. We are comparing this with the denominator. And just like before, we assume RFA to be 100 kilo, and therefore we find CFA to be 10 nanofarad. So from this circuit now, the numerator is now -1 over RA1 CFA. This we compare with the denominator, which is equal to -20. So this is equal to -20. And here also, now we plug in the value of CFA that we got from here, 10 nanofarad, to calculate RA1. So RA1 can be found to be 5 mega ohms. So we now have found all 3 elements for the pole circuit. So these are the 3 elements for the pole circuits. So this we found. Now we'll find for the zeros. This is the formula for zero. And in terms of the circuit B, we can write it like this. Comparing with, since this is S, so S is equal to 0 is the 0 point, and therefore we can write that this term is equal to 0. So this is equal to 0. Now here, instead of assuming resistance, we'll assume capacitance, because the resistance will go very high. The capacitance will have a limited value, so we assume a capacitance of 1 microfarad. So putting the capacitance value here, we know that anything to get 0 we have to divide this by infinity, therefore R1B has to be infinity. So we conclude that C1B is 1 microfarad, but R1B is infinity. And also the numerator is just 1 or minus 1 actually. From here you can see minus RB, RFB, CFB, and this is equal to minus 1, so minus minus cancels. So RFB C1B is equal to 1, and RFB is 1 over C1B, and plugging in the value of 1 microfarad, we get RFB to be 1 mega ohm. So these are the three values for the zero circuit. Now since the second circuit B and C represent the same transfer function S, hence they will have the same parameters. And so this is the answer that we get, and this is what is given in the book. This is for the pole circuit, and these two are for the zero circuits. And since the question has asked what is impedance, so he has just written the multiplication of the two. So parallel of the two. So 1 microfarad parallel with infinity. This is for the this case here, and this RF is 1 mega. Same case here, 1 microfarad parallel with infinity and 1 mega, and this is represented here. So if you want to draw the circuit, I have just drawn it like this. We plug in all the values. For R infinity, I have kept it open. I hope this gives you an understanding how to solve this synthesis problem. Thank you.